In the previous linear algebra video, we defined the determinant of a square matrix, and we saw one result which tells us that the determinant of a triangular matrix is the product of its entries along the leading diagonal. And let us start today's discussion by looking at some special cases of that result. And this is the first one. If your matrix in particular is a diagonal matrix where you have some entries along the leading diagonal which may or may not be 0, but all the off diagonal entries are 0, then also this is a triangular matrix. So by that result, its determinant would also be the product of these diagonal entries. In this second one, we have the n by n identity matrix, which is also a diagonal matrix in which all the diagonal entries are equal to 1. So the determinant will be their product, again because this is also a triangular matrix, and the product is just 1. So that's how the determinant of any identity matrix, I say any because the size may vary, the determinant is 1. More generally, if you have the same entry along the leading diagonal which is not necessarily 1, it may be 1, it may not be 1, then the determinant again is the product of the diagonal entries, which this time is lambda to the power n. Next we have this fact: if a row or column of a matrix consists entirely of zeros, if every entry is 0, then its determinant is 0. Actually, none of these facts is new to us because we have worked with determinants before in school also, and there we have already encountered all these things. But let's try to understand from our general definition of determinant how this is true. This is also something we have used many times in school when working with matrices and determinants. Whenever you see, in fact, this is what you want when you want to calculate determinants. This is what you always wanted, to somehow have a 0 row or a 0 column consisting entirely of 0 entries. Then automatically you do not have to do any calculation or anything, you write that the determinant is 0. But let's see how that is true. So let us take any n by n matrix, this A, whose ith row, jth column entry is the alpha ij. That means this is an element in this matrix algebra Fn. Then this is its determinant by definition. Determinant of A equals this sum. You already know, but still let's see once more what it was. There are as many terms in this sum as there are permutations in the symmetric group of degree n. Each such permutation corresponds to one term in this sum. This minus 1 to the power sigma is equal to plus 1 by definition if sigma is an even permutation, and minus 1 if sigma is an odd permutation. That is the meaning of this symbol. It is not literally the sigma power of minus 1, which anyway does not make any sense. And then we have these entries: alpha 1 sigma 1, alpha 2 sigma 2, sigma 2 means sigma of 2, and so on, alpha n sigma of n. Okay, and alpha ij are of course the entries of A. So what are we saying now? That if A has an entire row consisting of zeros, then the determinant would be 0. Actually what happens is that each term becomes 0 in this sum. How? Well, say the ith row of A is 0. Or if you find that a little difficult to think of, for the sake of being specific, say the first row is 0, is a 0 row. Now what are the entries in the first row? Alpha 1 1, alpha 1 2, and so on, alpha 1 n. All of these are 0. That means those alphas are 0 where the first index I is 1. How does that make this sum 0? Let's think of it. Say you arbitrarily choose a sigma from your group Sn. So that corresponds to this term. There is no need to think of this minus 1 to the power sigma. It's either 1 or minus 1. You look at the first term, alpha 1 sigma 1. Now no matter what sigma is, whether sigma of 1 is 2 or 3, it can be anything, okay, depending on sigma. This is 0. Why? Because all the entries in the first row are 0. So that means this term is 0, but sigma was any arbitrarily chosen element from Sn. So that's how all the terms of this sum are 0 and you get the determinant value as 0. That is if the first row consists of only zeros. Will it also apply to any row being 0? Yes. Say the ith row is 0. Where will you have alpha I something? Here, in every such term. In the middle somewhere, I mean in its place of course it will appear. You just start looking at the alphas and eventually you reach that entry which is alpha I sigma of I. Because the ith row of A consists only of zeros, does not matter what the second index sigma of I is. Because the first index is I, that alpha, that entry, alpha I sigma of I is equal to 0. And that term will appear in every such term, that entry will appear in every such term in this sum. So in general, no matter what I is, if the ith row is 0, then also all the terms in this sum are equal to 0, and that is how the determinant is 0. Alright, that is actually quite straightforward. But what about A having a column consisting of zeros? What about that case? Let's see. For the sake of simplicity, say we first think of the first column of A being 0. Okay, so what does that mean? It means that no matter what this first index I is, it can be any number from 1 to n. But if the second index j is 1, then the entry alpha ij lies in the first column and it will be 0, regardless of what I is. Alright. Do we find such an alpha here, no matter what term we are looking at in this sum? Say you arbitrarily choose sigma in Sn again as before, and you have got this term. Do not think of the summation now, just this term. In this term, do you have alpha something 1? Yes, actually you have that. Where? It depends on the situation. Do not forget that your sigma is a permutation. And what is a permutation? A permutation basically means it's actually is just a 1-1 onto function. Because it is onto, so among these sigma values that you see here appearing as second index of these alphas, there will be 1 somewhere. Why? Because 1 is also one of the numbers from 1 to n, and sigma has these numbers as its outputs. So obviously the number 1 must have come from somewhere via the function sigma, because sigma is onto. So we do not really know exactly where this 1 will appear as sigma of something, but it will appear somewhere. And wherever you have that alpha will be equal to 0, because it will be some entry in the first column. So you see that A having the first column consisting entirely of zeros gives the determinant value 0 again. And there is nothing special about first column. The same argument applies to any column of A consisting entirely of zeros. So that's how, if A has any row or any column having only zeros, then the determinant of A has to be equal to 0. Actually, you already saw this in school, but the difference is that in school you did not have this general definition of determinant. There you only work with 2 by 2 or at most 3 by 3 matrices. So you could verify this fact only for such matrices. But now we have it well understood for a general n by n matrix. Now our aim next is to look at those properties of determinants with which we are familiar and we saw them in school, which somehow are related to the rows of the matrix whose determinant you are calculating. So that is why we have this discussion. So again, let A be an n by n matrix whose ith row, jth column entry is alpha ij, say. Now for any I lying in this range from 1 to n, you can think of the ith row of this matrix A, which will have these entries alpha I1, I2 up to alpha In as a vector in Fn, in the space of n tuples over F. This may remind you of your school determinant classes, where we very often did this. We regarded the rows of a matrix, a square matrix, as vectors. And when we do so, then the determinant of A itself can be regarded as a function of these vectors. If you think of the rows as vectors, then the matrix is a stack of such rows, right? There is a first row which is a vector, and we are calling it V1 because the ith row is being called Vi when it is being thought of as a vector. The second row is V2, like that the bottom row is Vn. So we can then think of the determinant of A as a function of these vectors themselves. And when you think of determinant like that, many properties come out additionally. And we can adopt this notation, emphasizing the fact that we are thinking of the determinant of A as some function D of the rows of the matrix A. And in this notation, whenever we write V1, V2 like this, I mean whatever we write here, the first vector is supposed to mean the first row of the matrix, the second one will denote the second row, like that. We won't change the order. If we change the order, that will mean another matrix. Now next we have lemma 692, which uses this notation to say something about determinant, which depends on these rows. Say you have an n by n matrix A over F, and you have a scalar gamma from the underlying field. Now what is this that you are looking at here? It is the determinant of that matrix whose first row is V1, second row is V2, and like that I minus 1th row is V I minus 1. But the ith row is some row Vi times gamma. Okay. Actually, you may ask what these Vi's really are. These are not exactly all of them rows of A. The Vi's are rows of A, but you see here that it's not exactly Vi, it is gamma times Vi. Okay. So you are in fact looking at the rows of A here, except this ith row, which is not exactly the row of A. It is gamma times the row of A. If so, then the determinant of this new matrix, which is not A but it has been obtained from A by multiplying the ith row by gamma, the determinant of that matrix is equal to gamma times the determinant of A, because here all the rows are the rows of A, V1, V2. You see that the ith row now is no longer gamma times Vi, it is just simply Vi. So here you have, yes, all the rows are the rows of A. Or in other words, when you are calculating the determinant of a square matrix and you find that you are looking at a row and that row is something times another row, then you can take that something outside and calculate the determinant of the remaining matrix. Let's take one example and see this more clearly. Look at this example. Here we are looking at a matrix whose first row is 1, 2, 3. Second row is 3 times 1. These are not decimal points, okay. These dots denote multiplication. 3 times 1, 3 times 2, 3 times 3. And the third row is 4, 5, 6. You can take 3 outside the determinant like this and have the rest of the matrix inside the determinant. That's what this lemma is saying. But what is A, what is gamma here? A is this. This is your V1. V1 is 1, 2, 3. V2 is also 1, 2, 3. V3 is 4, 5, 6. So what you are starting with is that determinant where all the rows of A are there, almost all of them except one, namely this one. So in this matrix I is equal to 2. The second row is the one which is not exactly the row of A. Gamma here is 3 and gamma came outside. 3 went outside and the rows that you are left with are actually now all the rows of A. So that's how you can simplify the calculation of determinant if you happen to have a row in which all the entries are multiples of something common. That something common you can take outside. So that will reduce the size of the numbers and it will be easier to calculate determinant. So that is your lemma 692. Next we have lemma 693. So what about the proof of that? You are being urged to go through the proofs in the text yourself. And if you have any doubt, please let me know by writing in the comment section below. We instead look at the next lemma, lemma 693. So this lemma tells us about adding two determinants of matrices which only differ in one particular row. You can see here that the first matrix has these rows which are actually all the V's. V1, V2 like that, Vi minus 1, Vi plus 1 up to Vn. And then we have another matrix which also has almost the same rows as this matrix, V1, V2 up to Vi minus 1, but then the ith row is possibly something else, something other than Vi, so this is Ui. And then the rest of the rows are again the same rows. If so, then this sum is equal to the determinant of a new matrix where again these rows continue to be the common rows that we already have. But the ith row now is Vi plus Ui. What is the meaning of Vi plus Ui? Here you are adding two vectors, each having n components. In that sense, addition. Here also let's look at an example that will make it more clear. So you look at this sum of two determinants and the matrices involved are these. So they should differ in only one row, and that one row need not of course always be somewhere in the middle simply because we are writing Vi here in the middle. It can be any row. Here for example I have chosen that row to be the first row. So let's see the matrices. The first row in this matrix is 1, 2, 3. In this matrix however it is 3, 1, 5. You can see that the other rows are same. Same means corresponding rows are same. 1 minus 1, 5, 1 minus 1, 5. 0, 1, 6, 0, 1, 6. So what this tells us is that this sum will be equal to the determinant of a new matrix. And that new matrix is not the sum of these two matrices. No, we only have to add those two rows which are different. And That gives us what? 1 plus 3, 4, and add in what sense? Add as vectors. You would add the first component 1 to the first component of this vector 3, 1, 5. So 1 plus 3 is 4, 2 plus 1 is 3, 3 plus 5 is 8. But do not add the other rows which are same. You just write them. That's what this result says. How can you use this property? You can use this property to simplify your determinant calculation sometimes. If the entries are very large, you can break them up and write it as two determinants. It's not really very useful in that sense, but sometimes it may be useful in some special cases. The next lemma, lemma 694, is very easy to state. If two rows of your matrix A are equal, then the determinant of A is 0. You do not have to think of anything else here. For example, consider this determinant involving a 4 by 4 matrix. You can understand how complicated it will be to calculate this determinant if we just simply use the definition, write that sum sigma. Just think about it for a moment. How many terms will that sum have? As many terms as there are sigmas, where in S4, the symmetric group of degree 4. How many elements does that group have? What is the order of the group? 4 factorial, 24. So there will be 24 terms. But there is no need to do those things because the first row and the fourth row are equal. So by this lemma, you know that the determinant is 0. That's it. Next you have lemma 695. Interchanging two rows of a matrix A interchanges the sign of its determinant. And this simple example illustrates that. Determinant of this 2 by 2 matrix, where the first row is 1, 2 and the second row is 3, 1, will be the negative of the determinant of this other matrix which has been obtained by interchanging these two rows. Obviously here the situation is too easy, but you can apply this to any matrix. In particular, if you look at this matrix, although here the determinant is 0, I mean you can think of any other matrix which is somewhat large and say there you have something as your second row and something as the 24th row. Okay, so it is that large. If you interchange these two rows and then calculate the determinant of the new matrix, the new determinant will be the negative of the previous determinant. That's what this lemma tells us. And next we have this corollary which follows easily and naturally from this lemma, which tells us that instead of applying a single row interchange to the rows of A, we apply a permutation of the rows of A to A and obtain the matrix B. Then the determinant of A is either equal to the determinant of B or it's negative. And there is something else. Let me just say it. Where the sign is +1 if that permutation is an even permutation and is -1 if that permutation is an odd permutation. And the next result is theorem 691, and this becomes important when you have to calculate the determinant of a product of two matrices. So if you take any two matrices A and B in Fn, then the determinant of their product is equal to the product of their determinants. So calculating the product may be very difficult in itself, and then you have to calculate determinant. Instead, what you can do, you just simply calculate their individual determinants and multiply the two results. So that way your calculation has been made easier. This theorem has a corollary which follows quite easily from this if you just think about it. But anyway, we are not going to follow the proofs here. Instead, we focus on the results themselves and later on the exercises. So if our matrix A is invertible, then its determinant is first of all a non-zero field element, and the second thing is that because A is invertible, its inverse exists, and the determinant of the inverse is equal to the inverse of the determinant of A. And what is this inverse? This inverse is just the inverse, multiplicative inverse of this field element determinant of A, which exists because it's a non-zero field element. And then we have this second corollary also. If the matrix A is invertible, then for any square matrix B of the same size as A has, determinant of A B A inverse is equal to determinant of B. So this result just tells you that the determinant of any matrix and another matrix similar to it are the same. And this result allows us to define the determinant of a linear operator. Let's see how. Say you have a linear operator T on the vector space V. That means T is an element of this operator algebra A of V, and V of course is finite dimensional. And let M1 of T be the matrix of T with respect to some basis for the space V. Now if you change the basis, the matrix will also change. Say M2 of T be its matrix, that is the matrix of T with respect to some other basis. Then by theorem 632, you know that these two matrices are similar. That is, there exists a matrix, a square matrix C of the size equal to the dimension of V, such that M1T is equal to C M2T C inverse. So by the corollary 2, the determinant of M1T will be equal to the determinant of M2T. And that's how we can define the determinant of the linear operator T itself to be the determinant of any of its matrix, because all such determinants are, by this corollary, same. So it does not depend what basis we are using of the vector space to have a matrix first and then we are calculating the determinant. Matrices may vary, but the determinant will have only one value. So we can that way unambiguously define the determinant of a linear operator. There are a few other things that we will discuss in the next linear algebra video. So let me just end this video here itself. So see you in the next video with more things. Until then, this is me, Lucifer, from a mathematical group. Have a nice day.